sentence works, or what happens when you flatten an array. Here's another one on APIs and how they work, all told through the story of small robotic waiters who bring you the data you want. I also worked on a project called Just JavaScript, which I co-created with Dan Abramov. It's a JavaScript course that teaches the core mental models of the language through animations and diagrams. So we developed this visual language where we get every single piece of syntax to correlate to a specific visual shape. And we use the system to explain concepts like assigning properties or object mutation. The goal of all these illustration projects is to make complex technical topics relatable and easier to understand, which is a theme you're going to hear a lot about in this talk. In going through this process of transforming programming concepts into visual images hundreds of times, I've been forced to think a lot about the ways we represent and communicate complex programming ideas. And I've come to believe visual representations have a lot to offer us, more than we give them credit for. In this talk, I'm going to show you how visuals can make programming concepts less abstract, easier to understand, and more accessible to more people. I'm also going to show you why visuals are so special. It turns out to be relatively simple. Visuals bring invisible, abstract programming concepts down into the embodied world. The embodied world is where you and I live. Everyone watching this talk has a body, and you use it to interact with the physical objects around you, to move through space, and to experience events over time. Everything you know about the world is mediated through your body, and this fact is so fundamental we often completely forget it. And programming concepts are abstract ideas that do not live in the embodied world here with us. They're imaginary objects and functions. They exist in a liminal space that feels like it doesn't obey the same laws of physics as us. And we only interact with them through this disembodied experience of typing linear text instructions into a code editor. This is precisely what makes programming so difficult. We're trying to reason about and work with things that we cannot see or touch, when we are creatures who are evolutionarily adapted to function in a highly visual, spatial, and physical world. I'm going to argue that visuals are a big part of bridging this gap between our embodied human world and the disembodied machine world that we're trying to program in. So we're going to explore this topic through 3 questions. We're first going to ask, what's wrong with text? We're then going to explore what visuals can do that text can't. And finally, we're going to go on a brief tour to find out, haven't we already tried this? To ruin the ending, yes, lots of people in the past have explored ways to make programming visual. We're going to look at what's already been tried and what opportunities still lie ahead. So first, what's wrong with text? This is an important question to ask because almost everything we do in programming is expressed in text. This is how every app you've ever worked on looks. It's text arranged in lines going from left to right and top to bottom. Here's every documentation website you've ever read. Here's every blog post you've ever learned from. The balance of text to visuals in our industry is roughly 98% text to 2% images. All of our current programming languages, tools, interfaces, and documentation are overwhelmingly text-centric. You sometimes get a diagram here and there, but it's really slim pickings. There are plenty of historical reasons for this. This is a computer circa 1970. You'll notice the lack of screen. Until the 1990s, the only way to write programs was with linear text. This meant we established text as the primary medium for programming very early on. There are also plenty of logical reasons for this. Written words and syntax are an ideal medium for expressing abstract logic. It's quick to create, it's flexible, and it's easy to move between applications with copy and paste. You can pack a dense amount of information into a very small space. And you can be very specific about what you mean, which obviously matters when we're talking to computers who have no sense of nuance. So far, text has been working great for us in programming. But some of text's greatest strengths are also its greatest weaknesses. The abstract nature of text is what removes it from our embodied experience in space and time. When we write code, we're writing a set of hypothetical instructions to run on someone else's machine some point in the future in a place and time we'll never know about. This level of abstraction removes the physical, spatial, and embodied qualities that humans rely upon to understand the world around us. This can be good in some ways. When we write a function like fetch user data, we don't have to define the size, shape, or color of it. It's just a simple function floating in machine land. If you already know what this function is and how it works and where it's located, this level of brevity is great. But for someone new to programming, or even just new to your code base, who has no pre-existing mental model of how this might work, it's going to be really difficult to explain it to them. One of the easiest and most effective ways to make it comprehensible to them is to explain it in familiar terms, by using physical qualities they already understand, like size, shape, color, and spatial relationships, which might give us something like this to help explain what a fetchUserData function does. The visual doesn't have to be crazy complex or beautiful. Boxes and arrows work great. And we're certainly allowed to use text labels to make our imagery more clear. Visuals let us use our pre-existing embodied knowledge to show how programs work in a way that text just can't. So I've started to hint at the question we're going to look at in part 2, which is what can visuals offer us that we can't get from linear text? I think visuals reveal 3 aspects of programming that we're unable to see in text. They reveal fundamental metaphors embedded in our programming languages. They reveal spatial mappings that we use to reason about how our programs are structured and how data moves through them. And they reveal how our programs and data behave over time. All these things are implicit in the programs we write, but they're not things we can explicitly show in the medium of linear text. So let's start with metaphors. Just to make sure we're all on the same page, let's establish that metaphors are thinking tools that allow us to understand one thing in terms of another. So we have something we understand, thing A, and something we don't, thing B. And we map the qualities of thing A onto thing B. So if we say corruption is a disease, we map what we know about diseases onto corruption. So we learn that corruption spreads easily, is difficult to overcome, and can threaten the health of a society. Now, when I talk about metaphor in the context of programming, I don't mean the creative, fanciful metaphors you find in poetry and parables, like taking the road less traveled or wandering lonely as a cloud. We call these figurative or poetic metaphors. They're the sort we're warned not to use in technical tutorials because elaborate, poorly chosen metaphors can be more confusing than helpful. I'm talking about a much more fundamental type of metaphor that lies at the heart of all abstract thinking, including programming. These are called cognitive metaphors, since they enable cognition on a much deeper level. These cognitive metaphors are based in our embodied experience of the world. We have all these non-physical things we need to communicate to each other, like emotions and thoughts and ideas and programming concepts. And in order to understand them and talk about them, we use our experience of the physical world as a metaphor. If you look at the way we talk about abstract things, this becomes obvious. We talk about ideas in terms of light when we say, that's a bright idea, or that really illuminates the problem. We talk about emotions like they're objects. We say, he hid his jealousy, or she doesn't handle anger very well. We also use force and motion metaphors to describe experiences, like, I found your talk moving, it really touched me. Or we talk about programming ideas in terms of temperature, like hot reloading in React, and how the JavaScript landscape is heating up. This isn't a theory I've come up with on my own. These principles come from the field of cognitive metaphor and embodied cognition. They were first developed in the 1980s by researchers like George Lakoff and Mark Johnson, and has become a major area of research in cognitive science. These 2 books, Metaphors We Live By and Philosophy in the Flesh, are 2 of the main texts if you're curious to learn more. Just like every other abstract topic that we can't see or touch, programming relies heavily on these physical embodied metaphors. We have to because programming is a game of abstractions. When we run a JavaScript file, what we're really doing is telling a microchip to flip a bunch of logic gates using tiny electrical pulses. And programming tiny logic gates is very tedious and difficult for humans. So we've developed a stack of elaborate metaphors that make it easier and faster. Some people might prefer to call these abstractions. We simplify our binary code into machine code, which we simplify into higher level languages like JavaScript, which we simplify with GUIs. At every step of this process, we're trying to make the abstract machine world resemble our tangible human world. We move closer towards more intuitive embodied knowledge in the upper right-hand corner, the easier it becomes for us to understand what's happening in this system. Components in React are a great example of these embodied metaphors in action. Components are essentially containers, right? They hold sets of UI elements for us. Now, the CPU that's eventually going to render this card component on the screen knows nothing about containers. It only knows machine code and how to make the right pixels light up. The container is the metaphor that we humans need in order to manage and organize the code we write. The only reason you know what a container is because as a child, you dumped sand into a bucket and poured it back out again. And this interaction with the physical world of learning through embodied experience taught you that containers hold things, that they have insides and outsides, that they have boundaries. All of these concepts are essential and necessary for you to understand how components work in React. Let's take another one. In most JavaScript projects, we structure our components in a hierarchical tree, where everything is connected back to a single root component. And you know what a tree is from seeing thousands of trees. You understand that they have branches that spread out from a single root, and this understanding allows you to work with component trees in React. Again, we're borrowing from the human world to interact with machines in a way that is natural and easy for us. And you can probably see where I'm going with this. Since your understanding of the programming world is based on your pre-existing knowledge of the physical world, it would be helpful if we could make that explicit in the way we explain and represent programs. And visual mediums allow us to do this. So let's move on to our next visual quality, which is space. All humans with bodies have an inherent understanding of a large array of spatial concepts like up, down, left, right, in, out, big, small, deep, shallow. And just like we use metaphors based in physical objects to understand our programs, we also use this knowledge of physical space to talk about the structure and behavior of our programs. If you think about the way we talk about the internet, there are very clear physical directions to it. We upload data to the cloud above us and download files to our desktop. We look through a browser window. We browse web pages moving from left to right, so pages we visited in the past are on the left, and pages we're going to in the future are on the right. This extends to how we talk about development architecture. Our apps have directionality because they have front ends and back ends, and frameworks like React sit in the middle. Specifically in React, we use our understanding of vertical directions to think about how data moves. React has a hierarchical order to components. Parent components are above child components, and they pass data downwards, which means we also have gravity in React land. The idea of prop drilling is another one that suggests we're drilling downwards in order to pass data deep into the tree, so that also has depth. All of these examples show how we use our knowledge of the embodied world to talk about and understand how React works. When we create visuals that show these principles explicitly, it clarifies what we're already doing in our heads. Our final element is change over time. When we're working in a linear text editor, time is essentially invisible. We're looking at a static representation that describes a whole array of future events that may or may not happen depending on what button a user clicks or whether our data request resolves. We're forced to use our imaginations to predict what's going to happen in all those potential futures, rather than being able to see them in some form. Our current best technique for trying to see how things change over time is console logging data out along the way, which feels like trying to get a program to send signals up to the surface of a dark ocean where everything is being executed out of sight. We can't see anything happening down there, and we just have to keep asking for clues about how our data is changing. This doesn't feel like the best developer experience. This is again where visuals might come in handy, because they allow us to see multiple points of time within a single frame. They allow us to compare things side by side in a way that we can't with linear text. They essentially allow us to spot the difference. Let's look at the syntax for the useEffect hook as an example of this. So here's 4 different versions of the useEffect hook, which are each going to behave differently when they execute in the browser. The first has no dependency array. The second has an empty dependency array. The third has the dependency count. And the fourth also has count as a dependency, and it also runs a cleanup function. By just looking at these 4 versions of syntax, do you have any way of knowing how this function is going to behave once it loads into the browser? Specifically, do you know how often it's going to be called and when? Given the demographics of this audience, I bet you do, but it's because you've memorized the syntactical meaning here, rather than knowing because the answer is visible in the syntax. What we need to do here is compare 4 things that behave differently over time. So I've made a set of diagrams that try to visualize the difference between these 4 on a timeline. Here's our version with no dependency array. The useEffect function is called on every single re-render, regardless of whether our count variable updates or not. They're not connected. In our second version, where the dependency array is empty, the useEffect function is only called on the first render, and we still don't care whatever the count variable is doing. In our third, with count as in the dependency array, the useEffect hook is called only when count updates, and then it triggers a re-render. And in our final version, useEffect is called when count updates, and then it runs the cleanup function afterwards. This simple visual representation of how useEffect behaves over time gives us a much better understanding of how it works than the linear syntax is able to. The syntax doesn't reveal events in a sequence the way a graphic timeline can. So finally, part 3, haven't we already tried this? Obviously, I am not the first person to realize that visual mediums enable us to understand and reason in ways that are worth exploring in programming. The primary way people have tried to incorporate visuals into programming in the past is by sticking graphical user interfaces onto IDEs. These efforts all fall under the umbrella of what gets called visual programming. There have been many, many past attempts at this, with varying degrees of success. I'm going to quickly whip through a few examples so you get a sense of what's already been tried. This is Grail from 1968, which was one of the very first visual programming languages. This gave us text in boxes for the first time. Here's Pygmalion from 1975 that built on that box and arrow model. This is LabVIEW, which came out in 1986 and is used for systems engineering. We got a lot more intense about boxes at this stage. Here's a more modern example. This is Blueprint in Unreal Engine, which is used for 3D game development. And this is Origami Studio, which is a prototyping tool built by Facebook. You'll notice the node and wire design pattern is very popular in a lot of these. So there's lots of really promising stuff in these examples, but visual programming is still relatively niche. We've discovered a bunch of wicked design problems in it that are really hard to solve. These systems don't scale well to large complex projects. They sometimes use ambiguous symbols and unfamiliar interface patterns. They try to turn everything into a box, which takes up way too much screen space. And they can lead to literal spaghetti code, like this Figma prototype gone awry. These issues have led to a lot of skepticism about the feasibility of visual programming. Being an advocate for it often feels like being Gretchen in Mean Girls. Visual programming isn't dead, though. Funnily enough, the new no and low code movement looks suspiciously like visual programming under a new name. Many of the interface patterns that visual programming helped develop, like nodes and wires and direct manipulation, are visible in tools like Integromat, Zapier, and Webflow. Rather than trying to build Turing-complete visual languages able to reach industrial scales, we've tactically moved on to developing visual interfaces for specific use cases in programming with sensible constraints. Here's an example of doing this really well. Some of you might have used Stately AI. It's a fairly new visual interface for building state machines in JavaScript, where the visuals and the code are connected so you can change one and the other one updates. It's a perfect example of using visual programming for a very specific scoped context. It's not trying to visualize your entire code base. It's just helping you visualize states and the transitions between them. This also integrates with VS Code, so it's backwards compatible, and we don't have to bind to some new proprietary programming language to use it. This is exactly the kind of thing we need more of. I'm a huge fan of the visual programming agenda and finding more ways to build visual affordances into developer tools, and there are lots of smart, impressive people working on the problem. But in many ways, this is taking the hard route. Building a true visual programming medium will require overcoming a ton of design, culture, and engineering challenges. And it's frankly going to take a while. But there are ways we can advance this effort in the short term. We can simply sprinkle some visuals into our existing textual world. This means adding diagrams and illustrations into blog posts, documentation, and learning materials. If we're feeling brave, we could build plugins for our editors and developer tools that visualize very small, scoped elements of our programs. These are all essentially the low-tech, paper prototype way of building a fully fledged visual programming interface. So to wrap this up, here's the thing I want you to take away from this talk. We need more visuals that reveal metaphors, spatial meaning, and change over time to make programming easier for everyone. It will make it easier for you, since you're an embodied human who needs to learn abstract, complex programming ideas in order to do your job well. It will make it easier for all the people who don't currently know how to program but are trying to learn. And it will make it easier for people who aren't developers but need to understand what we do, like product managers and designers who can't read all the jargon in our text-heavy documentation. So, what can you, a humble but skilled React developer, do to advance that goal? First, explore the history of visual programming and some of the past attempts in the field. There's a lot of good previous art to learn from. If you are a current or future creator of tools for other developers, you should consider ways to build visual affordances into your libraries, plugins, apps, or frameworks. And finally, you should use and advocate for visual explanations in documentation and tutorials. That might mean making them for your own blog posts, or collaborating with designers if you work on larger projects with extensive documentation. We can set the bar low for now and try to budge this fake statistic up to like 10%. That was a lot of information packed into one talk. This was definitely a taster session to get you intrigued rather than a full meal. So I've put together a list of some things you can Google to learn more. These are also up on my website on maggieappleton.com/programmingpictures. I really recommend all the books by George Lakoff and Mark Johnson. Mind in Motion is a really wonderful book on embodied cognition by Barbara Tversky. There's a lot of talks by Brett Victor, who's a programmer who talks a lot about this stuff. I recommend you watch all of them. And there's really good resources on futureofcoding.org, which is about visual programming and the future of programming interfaces. And I recommend the book Visual Explanations for more practical advice on creating these if you really do want to go make your own diagrams. So thank you very much for listening. If you want to find out more about visual programming and metaphors in general, I write a lot about them on my website, and I hang out on Twitter @Mappletons, where you can tweet me. Thanks.